All right, ladies and gentlemen, a quick review video for Unit 19 DC circuits. I have the test here in front of me. I just completed it a minute ago. So I'm going to use that as well as the notes from this unit. I'll kind of go through everything, making sure that what I spend sort of the most time on is the stuff that's going to be on the test. There's plenty of other good stuff here in the notes, but we want to really focus this in just on what you are going to need for the test. So I want to start here with the idea of series circuits. Remember we said there are two basic types of circuits, series and parallel. And with series circuits, those are ones in which everything is lined up perfectly in a row. There is one way through the circuit. The current can only go in that one direction. There are no junctions, there's no splits. We don't go from one wire to two wires. We go in one straight path all the way through the circuit. So all of those components are arranged in one row. So here's just a little picture of what a series circuit looks like. As you can see, I'll kind of trace along here. There's only one path. We go from one resistor to the next resistor to the next resistor back to the battery. There's no split offs, there's no shortcuts, there's no anything. So one of the things you're going to be asked to do is to draw a series circuit with multiple resistors in it. It should look something like this. Remember, these two lines are a battery, and we use these little squiggly lines to be resistors. But just make sure that you have one path that goes straight on through. There should be no sort of cutting back of those. One of the big ideas that we saw, we saw some of the demonstrations with this. If you take one of those resistors out, so let's say, let me see if I can do this over here, like really big. Let's say I was on this one over here to just take out that resistor. I just removed it. If I do that, I have broken the connection from the positive terminal, that long line in the battery, to the negative terminal. There's no way for current to travel through this circuit. If that is the case, my circuit is now open. That means that if I do that, and let's say we had light bulbs or something like that, if I had light bulbs, all of those light bulbs go out. I don't have any electricity, any current flowing through this circuit anymore. There's no reason for it to. It can't get to that place of lower potential energy, that negative terminal. So it all stops. We don't get any current happening. Most people, the biggest misconception is, well, if I take out this middle one, the first one will still stay on, but the second one will go out. And that's not true. Again, if there's no connection from positive to negative, nothing happens. You get no current flow, which means that this first one doesn't light up, this second one doesn't light up either. So if you remove one of those components, maybe you take out a light bulb, take out a resistor, in a series circuit, it's completely broken. Nothing happens. There's no current flow. Any lights that are there go out. I want to skip ahead a minute here to the idea of equivalent resistance with a series circuit. So if we want to get the equivalent resistance, or what's called the total resistance a lot of the times for a series circuit, we just want to add all of the resistances up. So let's say, let me see if I can switch this back a little bit. Oh, right there, I think. Let's say I had this circuit and I had these two resistors in it, and I'm drawing with my mouse right now, so if it looks terrible, I'm sorry. But let's say I had a 20 ohm resistor and a 10 ohm resistor. The equivalent resistance, the total resistance of this circuit, is just 30. I just add those two numbers together. That is only for a series circuit. Parallel and combination circuits work a little bit differently, but if I have just that, just a series, just one of those straight shots, I just add those two numbers together. So if a question asks you what is the total resistance of a series circuit, that is what you are doing. If it gives you all of the different resistor values. And we use that quite frequently with resistance. We use that quite frequently with our circuits. Having that total resistance, that resistance subscript T, opens the doors to a lot of things. So a lot of these problems will first require you to get that total resistance, even if it doesn't ask you to. We'll get into some sample problems here in a minute. Beyond that, in a series circuit, this will come up many times. Current through any component is the same. The current that comes out of the battery, so the I subscript battery, is the same as the current that goes through resistor 1, is the same that goes through resistor 2, is the same that goes through resistor 3. Whatever current you get coming out of the battery is the same current that goes into every single one of those resistors in that series. Again, this is only true if it is in series with something else. When we get into parallel, it acts a little bit differently. So if you can find the total resistance of the circuit and you know the voltage of the battery, you can get that that current coming out of the battery. So this little equation, I'm going to edit it a little bit. I'm going to say that the voltage of the battery is equal to the current coming out of the battery times the resistance total. We are going to use V equals IR a lot, but it's not always necessarily with the battery. When it is with the battery, the voltage of the battery and the total resistance, you can find the current coming out of the battery. If you know the current coming out of the battery and the voltage of the battery, you can find the resistance total. And let's see, what else do we have here? Current flowing out of the battery comes up a lot. But again, all of the resistors get that same current in a series. And again, this, what I'm saying right now is only for a series circuit. When we get into parallel and combination, some of those rules go out the window, to be perfectly honest. So let me scroll through here a little bit. Voltage drops. If we know then our current, we're always going to know our current. If we know the total resistance of the battery and the current coming out of the battery, we can then find individual voltage drops in our circuit. So here we're going to use V equals IR. So this will be the voltage drop. So that a lot of times will be what you're looking for. If it asks you for voltage drop, you're looking for V. You don't have it anymore. Yes, the battery has a voltage, but if I'm looking, if you see here sort of the individual voltage drop, the question might say, what voltage drop occurs across resistor 3? In that case, you are looking for V. It is no longer 9. To do that, you're going to get the current through that resistor, but because it's in series, that is also going to be the current that comes out of the battery, and then you are going to use the resistance of that resistor. If you are looking for a voltage drop on just a resistor, you need to make sure that you use the resistance of that resistor, not the total anymore. And again, the current is constant because you know the total resistance and all the previous stuff. You could solve for that, get the current out of the battery, and solve for the voltage drop. And we'll get into it a little bit later as well. But just remember a way to check yourself if you're working in a series circuit. So I think I got one right here. If I had this series circuit, the voltage drop on R1 plus the voltage drop on R2 plus the voltage drop on R3 all have to add up to be 9. That's Kirchhoff's loop rule. If I go through a circuit, the voltage that I start with has to get completely used up so that when I go back through the battery, I end up with that same voltage that I started with. So that's a way to check yourself. When you get into the combination circuits, that idea is going to be a little bit more prevalent. But if it's just a series circuit, it's just a way of checking yourself. And the last thing we had is power. And again, this is P equals IV. If you're looking for power, let me just double check on the test. I think the only time it asks you for power is through a particular resistor. So it will not ask you for the total. But again, you're going to use for a series circuit, you would use that current that is from the battery and the voltage drop on the resistor. So here we go. I don't want that. We'll say that V is the drop on that resistor. So let's say I wanted to get the power for resistor 3. I would use the current that goes through the resistor 3, again, because it's series. That is the current out of the battery. And then I would use the voltage drop, which I just calculated using V equals IR, on that particular resistor. If I was looking for the power of the entire circuit, I would use the voltage of the battery, but because a lot of times you'll only be asked for the power on a resistor, you're going to want to use the voltage drop on that resistor. And again, we'll do some examples at the end. I just want to kind of get through a lot of the ideas first. And the second big idea we had is parallel circuits. These are circuits that have their own separate branched paths. It is a circuit that is a little bit more complex than the series. You can take many paths through the circuit, but we are going to have some rules that will follow for these. Again, here is a picture. You will be asked to draw at least one of these. Just make sure you've got the battery, and then if you see sort of these different square shapes where each resistor is on its own separate little path. Series, we said there is only one path. In this particular picture, we have three separate paths that the current could take, and there's some rules that go along with each one of those paths, some things that have to be true. First thing, just sort of a general idea, if we remove a resistor or a light bulb from a parallel circuit, we don't break the paths. We break that one particular path, but we don't break all of them. So if you notice here, let's say I take out resistor 1, there is still a path that goes through resistor 2 and back to the negative terminal, and one that goes through resistor 3. So if I take out that resistor, I actually keep the other lights on. They'll actually get more current they'll get the total resistance will increase, and they will get more current because no current will go down this path. Instead, it'll go through R2 and R3. So the circuit does remain closed. It does remain still functional. Here we've got our, some of the same ideas that we had with series circuits are going to still be there for parallel circuits. We still want to be able to get that total resistance, but we have to use a different equation in order to do that. So this says that we have 1 over the total resistance of a parallel circuit equals 1 over each of the individual resistances added together. Most people remember to do 1 over 100 plus 1 over 50, let's say, to get 3 over 100. And again, just type these in your calculator. Don't try to do it in your head. A lot of people will then say, all right, well then my my resistance is 0.03 amperes because I did this, and then I'm done. Remember that the total resistance, when you add up those reciprocals, you're getting 1 over the total resistance. So in order to get just your total resistance, what you're actually looking for, and that should be ohms, not amperes. Let's kind of cancel it out. You have to do 1 over that value. So in order to get my total resistance, I would take 1 over 0.03, and that actually equals my total resistance of that parallel circuit. Don't forget this last step. I imagine if anything goes wrong, that's what it's going to be. People will forget the idea that you have to take that last reciprocal at the very end as well. So I think that should be like 33 1/3 ohms. So taking the reciprocal sum, we're still going to use V equals IR, but with a couple of different little rules here. There's just another diagram. The voltage drop in all branches of a parallel circuit are the same. One of our rules, we said for any path between the positive and negative terminal, voltage drop must equal the voltage of the battery. So let's say I were to take this path through this first resistor. I don't get to go through any of the other resistors. Voltage drops only are going to happen at the resistor. So if that's the case, and I need to get from 9 to 0 in one move, it's got to be 9 volts. I've got to give up all 9 of those volts. So my voltage through R1 is going to be 9 volts. If I do the same thing through resistor 2, we're going to see that the same exact thing occurs. I only go through one resistor. I've got to give up 9 in that time, so it is going to be 9 volts. And you guessed it, one more time, 9 volts here for resistor 3. I only go through one resistor, so in that resistor, I have to give up all 9 of my volts. So when we have a series circuit, the current through each resistor is going to be the same, but in a parallel circuit, we actually have different currents, but the same voltage drops across each one. So the question arises, well, which resistor gets the most current? The one that's the smallest. So in this case, resistor 2 would. Think of it like if you're driving, you're trying to decide what road you want to take. You got to get to the same place regardless. You're going to take the one likely with the least amount of traffic. It's easier that way. If you're walking, down the hall, you're not going to try to go through a bunch of people. You're not going to just try to push your way through. You kind of find whatever path is going to be the easiest. That's the one of least resistance. We talk about, it travels through the path of least resistance. Well, this red path here is going to be that. So the lowest resistance gets the most current. Sort of backtracking to the series ones real quick. Same ideas. I kind of forgot to mention. So like here, they're all going to get the same resistance. I'm sorry, the same current going through them. But now the biggest resistor is going to cause the largest voltage drop. You don't actually have to do any calculations to say that, but you can prove it with the math. We could say that V equals the current is going to be the same on all of these, so I'll just kind of say a little line there. They're all the same through all of these. But if I've got a greater resistance, like I do here at resistor 1, my voltage also goes up. If I increase my resistance from 4 to 10 and I keep my current the same, my voltage has to increase. My voltage drop has to increase. So in a series circuit, the largest voltage drop occurs at the largest resistor. Get back to where I was. Check the test again here. So we're going to do a lot of the same ideas, same sort of rules. So if we want to know how much current flows from the battery, we're still going to do V equals IR. Let me see if I've got a little note there about it. Back it up here. Yeah, use Ohm's law that V equals IR with the total resistance to determine the total current. So I would say that in order to get the voltage of the battery, and again for parallel circuits, that is going to be the voltage drop on each individual resistor as well. The current that comes out of the battery and the resistance total here. If you're looking for that total resistance or you're looking for the current that comes out of the battery, use that equation. Make sure, though, that you are using the voltage of the battery and the total resistance to get that current out of a particular, use total current, not a particular resistor. If you want to get the current through a particular resistor, kind of like we said again before, lower resistances get a larger current. And if we want an individual current resistor, since you know the voltage drop, it will be the same as the voltage of the battery of a resistor and its resistance, because it's going to say, well, it's the 7 ohm resistor. Again, we can use Ohm's law. So here, if we want the voltage, and again, that's of the battery because we're in parallel, in strictly parallel. So then if we want the, let's say the resistance through, the current through resistor 2, we would then use the resistance of resistor 2 as well. We have to match those up. We have to be talking about the same resistor. So we're not going to use the total resistance this time. We're going to use the resistance of just that individual resistor instead. Combination circuits take both of these into account, and here's kind of where I want to get into some of the nitty-gritty, actual doing some calculations here. But I also want to talk a little bit about sort of ranking these ideas of, well, which one is going to be get the most current, where are we going to get the most voltage drop, what do these have to be equal to? But before we want to do that, we want to make sure we have a brief understanding of Kirchhoff's laws. The first one is the junction rule, the first rule or junction rule. If we have two wires, two paths that sort of sync up, that come together at what we call a junction, it's where you meet two wires together or more than two wires. So if you're looking at maybe a circuit that suddenly goes into parallel, this point here is what we call a junction. It's a place where we go from some number of wires, maybe one, to a different number of wires, maybe in this case two. So the junction rule says that whenever we enter a junction, whether it be two wires coming together, one wire splitting into multiple, two wires then going into two more wires, the currents that go in to that junction. So let's say we had some current going in here and it was 5. The current that comes out in those paths has to add up to be 5. So it could be 2 and 3, it could be 1 and 4, it could be 4.99999 and 0.00001. But those two paths have to add up. The same is true if I sort of go down into just one path. Let's say I knew I had 3 amps and I had 2 amps. This has to be 5 amps. So over here on the left side, we've got sort of an example of what might be more of a test-like question, where we've got 3 amps going into the junction, and then we know that we've got 7 amps going out and 4 amps going out. And the question is, in which direction and how many amps are on this wire X. So the way I like to approach it is to say that my current in, let me shrink this down a little bit so I can get more space. There we go. Current in equals current out. That has to be true. That is, as simple as we can say Kirchhoff's first rule, the junction rule. So going in, I know I've got 3, and going out, I know I've got 7 and 4. Well, 7 plus 4 is much greater than 3, which means that I have to have some other value going in on this side. So that's going to be my X. I know that my X has to be going into the junction. So when I simplify this down a little bit, you find that X equals 7 plus 4 minus the 3 from the other side. So that should be X equals 8. That means that 8 amps of current must be going into that junction on this wire. And the second rule, kind of mentioned it a little bit before, is this idea of the loop rule. The top version, again, is kind of the official version, but the way we've been working with it more is this bottom version down here. The sum of the voltage drops around any and every path through a circuit must be equal to the voltage of the battery. We sort of noted that with the with the parallel circuits, that any of those paths had to add up to be the voltage of the battery. So now we're getting a little bit into the idea of these combination circuits. And here's where I'm going to do more of the actual calculations and examples. So let me go ahead and get some just some numbers up here, and it's sort of doesn't matter. We'll say it's a 9-volt battery. This resistor, we'll call it resistor 1. It will be 10 ohms. Resistor 2, we'll make him 100 ohms. And resistor 3 here, we will say is 50 ohms. Looks good. So one of the things we haven't done as much in class, and we're going to do a lot during the review session tomorrow, is sort of these ranking tasks. There's a couple things that we can say about this. circuit without doing any math. And the first is we can rank the current going through each one of these resistors. So we know that coming out of this battery is some current, and when it hits this this junction here in the middle, it's going to split. We don't use up current. We can split it into two different places, but the current relatively remains constant. So if I have this junction, the question is which of these paths, we'll say the blue path or the green path, is going to get more current? And the answer is, well, this is a parallel piece of the circuit. Whichever path has least resistance. Well, this path down here has 50 ohms, and this path up here, well, these two are actually in series with each other. So if we wanted to get an equivalent resistance to just compare the two, we could say that this is really an 110 ohm path. So the current that is the most would be the one through resistor 3. It is going to be the greatest of those resistors. And like I just said before, resistor 1 and resistor 2 are both in series. There are no junctions here in the middle. The path just goes straight through them. So resistor 1 and resistor 2, because they're in series, are actually going to get the same resistance. I'm sorry, not resistance, current. They're different resistors. But we'll say that the current going through each of them is going to be the same. And that's 2, not 3. So being able to do that is a piece of the test. There's a couple questions regarding that idea of being able to say, well, which one gets the most current, which one gets the least current, and sort of organizing those ideas. If we were then to put, we'll say, a resistor 4 down here, and let's say it was just, let's say it was 1,000 ohms, some very large number. We have the current that comes out of the battery is going to be the maximum current. The most current you can get is the current that comes out of the battery. From there, you're going to split it, multiple times if you got parallel sections, but the current out of the battery is the most. So if we take and we split it here into these different pieces, when it comes back at this junction, it comes back to exactly what it went into that junction with. It is again the current that came out of the battery. So when it gets down here, it's the current of the battery. If we're in series, the current of the battery is the current that goes through that resistor. So in this case, if we had this resistor 4, we would say that the current through resistor 4 is even greater than that one. And let's say we had a 5th resistor, and we could say something like resistor 5, and it is just 1 ohm. It would have the exact same current as resistor 4. Those two are in series with each other, so because of that, there's no way to get rid of any of that current. We can't get rid of current. We use up voltage. We do not use up current. So this idea of ranking these, being able to say this is bigger than this, I don't necessarily know what the numbers are, but I do know what those are related to one another. I'm going to clear this off a little bit, kind of back up through some of this, and get back to where I was. And then we want to also be able to sort of rank a little bit or say some stuff about the voltages. So in this circuit, we have two paths. We'll call it the red path that goes through this bottom section, or the blue path, which goes through this top section. In both cases, they have to add up to 9. Because I start with 9 volts coming out of my battery, each of those paths, Kirchhoff's second rule, says that each path has to add up to 9. Because this bottom path, the red path, only goes through one resistor, that resistor has to give up 9 volts. So 9 is equal to the voltage that goes through resistor 3, the voltage drop on resistor 3. If I take this top path, I'll write it as blue again. If I take that top path, between these two, I have to give up 9 volts. So this one could be 0.9 and this one could be 8.1. This one could be 4 and this one could be 5. I'm sorry, 4 and 5. It doesn't matter, you could do the calculations and figure it out, but the voltage drop between the two, if I added those two up, voltage on 1 plus the voltage on 2, it has to equal 9. It has to equal 9. Because I don't have any other resistors to get rid of some of that current with, these two together have to be equal to 9. There are no other options there. So being able to sort of rank those, compare them to the voltage of the battery is a very valuable skill to have. So let's back it up one last time and get some total resistance. Hot dog. Oh, no, that's a different one. Let me get rid of some more of this gunk. There we go. So with these these combination circuits, we want to be able to get the total resistance of the entire circuit. So I need to do a series of equivalent resistances like we've done before, where it's either working with series or working with parallel, one at a time, to say, all right, I can sort of combine some of these and get a total resistance for the entire circuit as a whole. So the first thing I noticed with this one is that I do not have any resistors that are in series with the battery. There's no resistors that go straight in with no junctions to the battery. If that is the case, then I want to start with these two guys in here. I want to make these two that are in series into one. So because those two are in series, so R1 and R2 are in series together. There's one path between them. There's no junctions in between them, which means that R1 plus R2 gives me the resistance of that series section. I'll put a little subscript S there, which means that 110 ohms is the equivalent resistance of that series section. What that is saying is that I could treat this, for the sake of what I'm doing, as if I just had one resistor that was 110 ohms. I'll call it the resistance of the series section. So now I've taken those two, I've made them into one, and now this right here is just a parallel. So I can use that parallel equation, the 1 over RT, the total resistance now, is 1 over 110 plus 1 over 50. I don't know what that math comes out to be. Let me grab my calculator. Uh, 1 over 110 plus 1 over 50 gets me 0.0291. But again, I want to make sure I take the reciprocal of that. I want to take 1 over that value to get my total resistance. I would take 1 over 0.0291. And I'm getting about 34.4 ohms. So that is my total resistance of the system. And then I can do some of the same stuff. I can get my current coming out of the battery. I could, if I had some other information, I know my voltage drops, I already got those, so I could get individual currents on those resistors. And it all comes back to V equals IR. Almost everything we're going to do is V equals IR. Just remember that, let's say I had, let's go ahead and get the total current that goes out of the battery. So we'll say that the voltage of the battery equals the current out of the battery times the resistance, so the resistance total. So if I take now and scroll down, I had a 9-volt battery. I'm looking for my current out of the bat, and I have 34.4 ohms of resistance. If I divide 9 by 34.4, I get about a current of 0.262 ohms. Just kidding, it's amps, not ohms. So that's my current that comes out of the battery, but notice that none of these resistors, and I'll put the other one back here now because if I was going to talk about a particular one, put this guy back where he was, get rid of that, get rid of that, and I think these were 110. None of these resistors actually get that current because we have this junction. Now if I had a resistor down here, it would get that current. If I wanted to find these currents, I would have to find the current in one path and then use that junction rule to say, all right, if 0.262 was up here, and let's say it was 0.2 on this path, the current through here, through both of these, would have to be the difference there, so 0.062 amperes, and then I could use that to find voltage drops, and I could find power after that. We will go through a great deal of examples in tomorrow's work. That'll be most of what we'll do because of this video is here for a lot of the other stuff. I would suggest if you're trying to get ready for the test, those last two worksheets are very good. They go through a lot of the stuff. It might even be a little bit of overkill, but those ideas are really strong on those two worksheets. So I would suggest those for your studies. Other than that, just make sure your packets are done for Wednesday when we have this test. As always, I hope this was beneficial to you. It's about 6:30 on Monday. I'm still here at school because I've been putting this off as long as possible, but that's all right. Again, hopefully this is helpful, and I will see you all tomorrow.